let's see, I came up with another interesting bioscience question I ran across, or my kid told me, is if you see an endangered animal eating an endangered plant, what are you supposed to do about it? That's like a legitimate bioscience question. If I were teaching bioc here, that would be like question number 1. It's like bioethics. Okay. Okay, so one more topic we need to cover is how to calculate the moment of something a little bit more complicated. Okay, so we won't go back to that one. Good questions. Come to office hours. We'll figure it out. Somebody asked about that Greek swirly letter. I don't know. I think you might mean the alpha, angular acceleration. Okay, there's one more thing. What if this happens? You want I, but not through the center. This is on your homework, actually. There's one like this on the homework, and I think it'd be fair game for the exam, because you don't have to do calculus to get there. But say we have a disk like this. Right, here's a disk, radius r, okay? And we know the moment of inertia around that, right? I around this axis, 1/2 mr squared. It's on your formula list. You're good at things on your formula list, okay? But what if I want to rotate around this axis? I equals what? Okay, so there is a simple formula that will help you see the moment of inertia around other axes. Okay, it's called the parallel axis theorem. Not around any axis, but around certain axes. And it's a theorem, but don't be afraid. It's not. We're not going to prove it. So parallel axis theorem basically says, well, let's just write it. The moment around the parallel axis, right? This is the parallel axis. And this is the center of mass axis, right? Because this symmetric axis that you know goes through the center of mass of the disk. Where is the center of mass of the disk? It's in the center, right? It's a uniform disk. It's a circle. We said usually for uniform symmetric things, it's in the middle. So if you can come up with an axis parallel to one that goes to the center of mass where you know the value, then you use this. The moment around the parallel axis equals the moment around the center of mass axis plus the total mass times the distance squared. Okay, where the distance is between the two axes. Okay, so let's label all these. This is the moment, and I'll tell you the tricks. Around parallel axis. That's that one. This is the moment around the COM, and I'm going to put in parentheses from the table. Okay, that's the one from the table. You look it up, and you see the line going through the center of the disk, and it's 1/2 mr squared, just like he said. And this is simply the mass times the axis to axis distance squared. That looks horrible, okay? So you may look at this and say, why didn't you call this R? Like, this is a confusing thing. You'd say, well, if I put this here, or you might even see it written in some books as I parallel equals I center of mass plus mr squared. But they're saying R is a distance between these axes. It doesn't have to be equal to the radius of the disk. If you put your rotation axis on the edge of the disk, which you often do because you usually have to be touching it to have something pull it around, you often do end up with an R there. Like in this problem, the way I drew it. Let's calculate it then. So I here, let's go ahead and calculate it. It is the center of mass value, 1/2 mr squared plus m d squared, but in this case d is r, because I'm on the edge, r squared. I'm going to put edge in parentheses there with an exclamation point. That's the reason that's r and not d. In every problem you do, that won't always be the radius of a disk. It might be anything. It could be anything. I could have asked you, what's the rotation of this about this axis way around here? And you just put in a meter. Right? But in this case, if you're on the edge of the disk, then it's just 3/2 mr squared. And that's it. 3/2 mr squared is the answer. So you can do that for a sphere. If this had been a sphere, you just put 2/5 mr squared here. And you'd be the same distance from the center of the sphere. Right? So the distance between this axis and the axis of the center of mass. Okay? So that's something we use. That's important in rolling motion of a wheel, which maybe we'll get to next week, or we're going to cover that more when we do energy. We'll do rolling more when we do energy. But you can imagine, if you're thinking about how a wheel rolls, we said, in the lab frame, in the real frame, it's rotating around at the bottom of the wheel. It's rotating around the center in the translating frame. But if we're talking the lab frame calculation, it's rotating around this axis. And that's exactly what this is. Right? That's the moment for going around the edge of the radius. Okay.